Today's topic, it is our first episode in our educational webinar series, and we will be talking about how we hear sounds and in some way talk about what we are as an acoustic transducer and how we behave. My name is Jacob Sondergaard. I will be your host today, and I'm excited to take you on this journey. So the motivation for putting together this slide deck and kicking off our educational web seminar series is because later on in the series, we'll be talking a lot more about the nuts and bolts of doing telecommunications testings. But at some point, we figured before we can start getting to that stage of actually doing the physical testing with devices, basically the image you see here in the top left, before we can get to that stage, there's some fundamental underlying knowledge that we should be discussing, basically this stuff here on the right. How do we act in a sound field? What is the purpose and function of our body, our ear, both the outer, middle, and inner ear? And how can we potentially use that to our advantage when we are designing acoustic audio telecommunications products? So with that being said, today's agenda we'll go through the physics of human hearing in pretty in-depth levels, and then we'll get to talking about some of the anatomical features that really govern how we perform in the sound field. The biggest thing, of course, is our acoustic transducers, the human ears, and we'll talk about the individual parts and how they influence our sense of hearing. And then finally, we'll get on to a comparison of what we know about the human body and how that has been translated into the test gear and setups and procedures that we currently have on offer in the marketplace. Now, let's start with a joke. The joke is, I'm sure you've heard it, but the whole, if a tree falls in a forest and nobody's around to hear it, does it really make a noise? You know that old saying and that old idiom. We won't necessarily start with a joke, but we will start with an event, an acoustic event somewhere in the far field. That acoustic event triggers a series of acoustic waves through space, and then here we are, a representation of us somewhere else, and we will eventually be exposed to those sound waves from that event, and our ears and our bodies and our brains will interpret that and basically try to locate the sound as well as identify the sound. Now, what is interesting is that our physical shape and size will affect how the sound waves behave in and around us, and that response is what we call the head-related transfer function, or HRTF. So when you talk to us, we will sometimes throw out that acronym for HRTF. The HRTF is hugely important when we're talking about things in the far field, like speakerphone products or conferencing systems. You have to take those effects into account. Now, to put some more detail onto that, if we take a microphone, a reference microphone, something like a 1/2 inch or a 1/4 inch reference microphone, so very small relative to a human body, but you put that in a free field, sound field, and you expose it to sound waves, a sweep going from, let's say, 100 hertz all the way out to 20 kilohertz, roughly the range of human hearing. What you see is, because the microphone is so small relative to the wavelengths, that the microphone will have little influence on the sound waves at the location where the microphone diaphragm or membrane is located, where it actually picks up the sound. So doing some quick back of the napkin math, we know that at 340 meters per second, 100 hertz, we're talking about maybe a wavelength of 3 meters. And at 1K, it's about a meter. I'm sorry, about 30 centimeters. And at 10K, we're down to about 30 millimeters. So you can see that even a 1/4 inch mic, something like a 6.35 millimeter mic, is still relatively small compared to the wavelengths out of these frequencies. Now, the best way for me to illustrate that in a different way is if you put a stick into the sand at the beach and you have a wave rolling up over it, the wave is much, much bigger and larger than that stick in the sand, and so will easily encompass and envelop and blow right past that stick without really causing much of a ripple. But if you had something large, let's say like a breaker wall or a jetty or a pier, you'll notice that as the waves crash up against the pier, you will get all kinds of reflected waves, diffracted waves, and other disturbances in the waves from the ocean. Similar thing with the microphones, except we're talking about very small things. Now, on the bottom side of the graph, what you'll notice here is these are the curves for a human being in a sound field. We are decidedly not flat. So because we have a specific height and width and shape to us, the acoustic pressure that is measured at our eardrums is going to be something along the lines of these curves, depending on the sound field that we are in. Because we are a larger object and because we have much larger interaction with the sound waves. And you can see based on this frequency response curve, you can sort of guess at our main physical dimensions. Like we have this major peak here at 3,500 hertz. And then likewise, we have effects down at the lower frequencies, about 1K and 2K. And you can start to extrapolate where those frequencies correspond to distances on our bodies. Now, the keenly attendees that were paying attention here noticed that the graph was, of course, upside down. And what I had done here was just to show you that if we wanted to equalize the response at the ear, assuming a flat source, we would have to apply this type of correction curve to get a flat response at the eardrum, or as if we were using a very, very small microphone and there was no human body in the sound field. So that's the fundamentals of an HRTF and the effect that the human body has on an acoustic soundscape. Now, let's go one step further here, because as the sound actually travels to us and starts interacting with us, we have to look at the human body from an acoustic perspective. Obviously, our body serves many purposes, but from an acoustic perspective, there's a lot of interaction, and that we use those interactions innately to help us identify and localize sound. And sort of the first question to you guys is, have you thought about how we differentiate between sounds coming from in front of us, but from in front and up and in front and down? There's obviously a big difference. And one of the biggest helpers to us are the reflections that occur off the shoulders. We're obviously very asymmetrical beings in the horizontal plane. And if you draw a horizontal line right around our ears, it's clearly noticeable that we have a lot more body mass below our ears than we do above our ears. And we're using that. Our brains are using that information, that acoustic information, to help us differentiate between sounds out in free space. Likewise, the ear-to-ear distance, along with some of those spectral shapes and changes that will occur at each ear, helps us localize sound in terms of angles to either side. Two of the main things that we talk about today, and people talk about in general, is the ITD and the ILD. ITD stands for the intraoral time difference, so the arrival time difference at either ear. And ILD, similar thing, but we talk about the intraoral level difference. So there are also level differences, and we'll talk about the shadowing effects of the human head. Now, if we dive in and we start talking about the intraoral time difference, the chart on the left will basically tell you in microseconds roughly what the arrival time differences are as you move from point A and then around in a circle to point B and all the way back behind the head to, let's say, point C. So you can see at point A, the arrival time should be 0, right? The sound waves will travel from point A, arrive at the left ear and the right ear at exactly the same time. And then as we move from A to B, you can see the arrival time differences, the delta between right ear and left ear, start to increase until it peaks at roughly 600 microseconds. So the sound waves now here from point B, you see we have a straight shot right at the right ear, but the left ear, we have to wrap around our heads to hit the left ear. And then as we move further back, we end up with basically 0 microseconds or 0 seconds difference between the left ear and the right ear. That's part of what we use to identify the angle of incidence of the sound event. Now, before we get too excited about this, there is the known problem of the cone of confusion, where, as you can maybe quickly identify, at 0-degree incidence and 180-degree incidence, we have 2 sound events or interaural time differences at exactly the same, i.e. 0. And so what the human brain is conditioned to do through many years of evolution is to think if there is some event that occurs with an ITD of 0, and we don't have any visual cues to help us, or any other cues like the ILD, and I'll get to that in a minute, but if we have no other cues to discern where is the sound coming from, our brains will automatically think, oh my goodness, there's a saber-toothed tiger right behind us and it's ready to pounce. And we have this cone of confusion where we're not sure if the sound is coming from directly in front of us or directly behind us, but our brains will trick us, or in a sort of defensive mechanism, trick us into thinking it's by default behind us and it's scary and we have to get away from it. Now, why are we mentioning this and why are we talking about this? Because let's say you're in the business of conferencing devices, or maybe even better yet, augmented reality devices, not necessarily the visual ones, but the audio ones, presumably why you might be interested in this webinar series. The audio products that are able to synthesize audio within the current acoustic environment, or even just playback audio. Let's say that you are going to synthesize a sound and you want to just put it right in front of the user, but if there's no visual cues to associate it, our brains are going to get confused. And therefore, it's much better if you can, in conjunction with other cues, maybe put a slight motion to the sound source, even if it's just from maybe +2 degrees to +5 degrees, something like that, to give our brains a little bit more information to place the object in space, than rather just making it appear at 0 with an ITD of 0, supposedly right in front of us, where our brains could easily get confused. Now, if we jump to the next slide and keep all that information in mind, you'll see that for the interaural level difference, it's not quite as straightforward as the ITD, because there are some frequency components that we have to take into account. At very high frequencies, we end up with a shape that looks roughly like what we saw for the ITD. At 0-degree incidence and at 180-degree incidence, we're basically seeing the same levels of both ears. And then as we traverse that space from directly in front of our heads to the right side and then around the back, you'll see that the delta between the right ear and the left ear will increase until it peaks at about 25, 30 dB and then back down again. Now, at lower frequencies, unfortunately, we are not as lucky. And again, we go back to how the HRTF and how the human body behaves in the soundscape. But what we see at lower frequencies is sound waves that are very, very long. The wavelength is very long. Our head is relatively small. And so if you imagine that stick in the ocean there, the stick in the sand, these waves are going to just pass right by our heads, right around our heads. There's really not going to be much disturbance or shadowing effects occurring at the far ear. And so we end up with roughly the same level at both sides. Now, in a previous job, I was fortunate enough to do some studies on acoustic pressure from rifles. I don't know, it probably doesn't have too much to do with what we're talking about today with telecommunications, but it was very fascinating that if you are a right-handed shooter, I don't know how many of you can relate to this, but if you are a right-handed shooter and you have a rifle and you're tilting your head a little bit towards the rifle, essentially exposing your left ear a little bit forwards and towards the muzzle, and the right ear a little bit backwards and towards your shoulder, if you can picture that for me. When we measured the levels at the ears when somebody pulled the trigger, we noticed that the left ear had about 10 dB higher SPL, sound pressure level, than the right ear. So we ended up seeing the shadowing effects even for something like a rifle. And you can sort of guess here, based on the angle of incidence and the rotation of the head and holding a rifle, imagine doing that, and roughly that 10 dB difference, that we're not talking about, the worst case scenario, the noise source being completely at 90-degree incidence, but we're talking about something like a 30-degree rotation of the head in order to get that 10 dB difference. So it's very evident and it's very obvious. Now, what can we do about something like the cone of confusion? Because the ITD and ILD curves are roughly the same. Fortunately, what the human brain and body is good at doing is, if you rotate your head, if you tilt your head, you're changing the axes of where these graphs live and operate, and it gives you a higher certainty in localizing the sound. And again, you can use these curves to your advantage and your knowledge if you are synthesizing. Now imagine, as an example, you have a hearable type device. So something like, Doppler Labs, Alpha Audiotronics, New Hera, Bragi, Jabra. There's a bunch of companies that are working or were working on this hearables type space. And you want to you're on a phone call with somebody, but you're also getting, let's say, navigation prompts that are sort of overriding the conversation. Rather than just maybe sort of muting the conversation a bit and just completely overriding with binaural stimulation, why not have the conversational partner rotate their virtual sound location off axis and then maybe rotate in the direction of the navigation prompt, and then once the prompt is done, you can rotate the conversational partner back and front. Little things like that you can play with to enhance the user experience of something like a binaural product like that. Likewise, if you're in the conferencing space and you have a three-way conference call, or let's say you have a regular call, one-on-one, and a third party joins the call. What if each of those parties were then acoustically split so that the first person that joined the call now gets rotated 30 degrees off to one side, and the second partner that joined rotates 30 degrees off to the right side? Using this information, you can project their voices at the ear location with pretty high degree of confidence so that they appear to be off at one particular angle and maybe separates them a little bit more. This is just food for thought. Now, going back to the HRTF, what we're showing you here is the measurements done on an artificial head, which was free field equalized, and then exposed to a free field source, so just a speaker in an anechoic chamber. And then as we rotate the head, you can see down here on the spectrograms, we have the FFT response, magnitude are the colored plots, and then we rotate in angles of degrees, starting with 0 all the way around to 180 degrees. What we see on the left ear, as we start rotating the head in the space, that at higher frequencies, in particular, we see a loss of energy at the far ear, whereas that tends to increase at the near ear at higher frequencies, which corresponds to what we found with the ILD curves, that the levels and the level difference at higher frequencies will be a lot more pronounced than, say, at the very low frequencies. You can see here, basically about 800 hertz and below, we're not seeing a huge difference between the two, whereas the difference is very noticeable at the higher frequencies. So just to give you a sense of how much of a difference, you can see out at 1820K, we're talking about minus 25 dB on the left here and plus 15. We're talking about almost 40 dB right here. So you have some space to play with if you are interested in synthesizing sounds. Now let's step into the ear. So that's just generally about the human body and the HRTF. Fundamentally, it's a nice satellite dish that funnels sound primarily from the front to the ear canal for later processing. Obviously, our ears, our pinna, are also asymmetrical, both in the horizontal plane, that helps us a little bit with localizing sound in the up-down direction, but also in the vertical plane, which helps us localize sound in the front-to-back plane. The sounds that are from the front are amplified just through the shape of our pinna. And I don't know if you guys do this sometimes, but if you have a hard time hearing something, you can kind of cup your hand up against your ear and expand that satellite dish a little bit, and you'll have a greater time hearing things from the front. Similarly, but in an opposite manner, sounds from the rear are attenuated. Human beings are generally very forward-facing creatures. Our eyes on the front, ears are generally focused towards the front, same thing with our mouth. And so we are very focused towards sound that are coming from the front. Now, the cool thing about acoustics and the sense of hearing is we do have 360-degree sense of hearing, right? We still hear things from the back. It's just the slight differences in levels and spectral content will allow our sophisticated brains to determine where the sound is coming from. Now, if we step into the middle ear, this is a surprisingly simple construction, but it actually serves quite a lot of purposes, right? So the main thing is we have a whole bunch of sound energy coming down the ear canal, and it hits the eardrum on the tympanic membrane, and it then transfers through the three smallest bones in the human body, which is the stirrup, the hammer, and the anvil, and then goes into the cochlea for actual processing and interpretation. And so what we see here is there's a couple things. Number one is there's a change in physics. We go from vibrations or sound or pressure in air to vibration inside the cochlea. We go from a change in medium. Our ear canals are filled with air, whereas our cochlea, so this snail type organ, the cochlea is actually filled with liquid. And we likewise go through a change in amplitude. So the pressure in the ear canal and on the eardrum is relatively small compared to the pressure on the window to the cochlea. So that pressure here is actually upwards of a factor of 20, and that's what the three bones here helps us do. Now, I guess the best way for me to draw an analogy to this is a little bit like a person standing in high heels, right? If they were standing flat-footed or barefooted, they would exert X amount of pressure. But if they put on a pair of high heels and we just measure the pressure right under the heel, you'll get a much higher pressure. And that's a little bit the same with this conversion that's going through the middle ear portion. Now, there's a couple cool safety features built into our middle ear. The first one is if we are exposed to a very loud sound, there will be a contraction in our middle ear that causes a temporary damping effects of all future sounds. Now, there's a couple key research areas where this is being applied. Number one is from a military perspective. As you can imagine, soldiers that go into theater of war end up being exposed to a lot of impulse noises and high pressure, high SPL events. And if there is a way to voluntarily trigger the middle ear reflex when there's a known high impulse event coming, you can potentially cause that damping effect and thereby reduce the risk of hearing loss. And so one of the things that they're looking at from a military perspective is, can you trigger your own middle ear reflex, for instance, right before you pull the trigger? And therefore, because you have control over when you pull the trigger and the known muzzle blast from the gun occurs, you could potentially dampen your own exposure and maybe forego the need for having, earplugs or other sophisticated devices in your ears that could influence your ability to localize sound or just hear in general, like enemy footsteps up ahead and things like that. So there's a lot of research on that side of things. In the consumer side, there's also been some research and actually an implemented solution by, I believe, Mercedes-Benz, where they did the same thing in that in a vehicle, when they were able to detect that a crash was imminent, the audio system in the vehicle will actually play out a loud, although not deafeningly so, but a loud impulse to trigger the middle ear response right before the crash of the vehicle. Because, knock on wood, I've never been in a high-speed vehicle crash, but if you have, or if you've studied them, or if you've looked at them, not only are they hard on the human body, they're also incredibly loud, and you have things like airbags going off in the vicinity. It's a loud acoustic event as well as a violent physical event. And so what Mercedes-Benz was doing is they were in an effort to just salvage whatever you could from an event like that, even if it was just a human hearing a little bit better. They would purposely play out an impulse that is loud enough to trigger the middle ear response, thereby potentially saving some people permanent hearing damage as a result of a high-speed vehicle crash. So it's pretty interesting stuff, and if you're in that space, definitely something you can look into. Now, another thing, I think everybody's been aware of this, and that is our ear also has a safety mechanism built in if we're exposed to very large pressure change or a DC change, and that is very commonly observed if you're in an airplane. And maybe if you have a little bit of a cold or just you haven't equalized your ears quite yet, you'll notice that pressure sensation on your ears or in your head. And if you don't equalize your ears right away, try just listening to your environment. Listen to yourself talk. Listen to your seatmate talk, or play some music back over headphones, and tell me how different the frequency response or the frequency content is of all that sound now. And that, again, is a little bit of that decoupling mechanism that occurs inside the middle ear. There's an active event in the middle ear that, under those high pressure, low frequency events, also decouples your eardrum from the window of the cochlea a little bit to help protect your ears, so there's no potential overdriving of an eardrum or an overdriving of the cochlea. So it's pretty fascinating stuff. Now, for those of you in the automotive business, maybe this helps you, maybe it doesn't, but what I like to consider, for you to consider, is that the middle ear is in some ways a little bit like an automotive engine / transmission, and that we're going through this change in physics from, combustion occurring inside the piston chamber to a rotational action at the wheels. We're going through a change in medium, obviously from air to liquid to kinetic energy, and there's definitely a change in amplitude going through the transmission. So as the pistons drive a crankshaft, you go through a transmission that maybe steps up the rotation. So maybe that works for you, maybe not, but on some fundamental level, that's what the middle ear does for human hearing. Now, on this next slide, I don't want to spend too much time talking about this because it isn't technically acoustics. But if you've ever been to an audiologist and had an audiogram done, I hope you have. It's a pretty neat experience, especially if you work in audio and acoustics. But you get handed a pair of headphones and a little clicker. You get sent into the listening booth, and they will play tones at different frequencies, and you have to press the little clicker whenever you hear it, and they can figure out basically how much potential hearing loss have you incurred, or how good is your hearing. Now, if you go to some audiologists that have, or they work at teaching universities, you might get lucky to have one of the students there maybe apply a bone conductor, or worse, I guess, if the audiologist suspects that you have middle ear damage, they will actually put a bone conductor on you. It's a little bit like a headset, but rather than an acoustic transducer, there's a little vibrating transducer, and they put it not on the ear, but right behind the ear on the mastoid. I don't know if you guys want to poke yourself right behind the ear, but you can kind of feel there's a hard bone back there, part of your skull. It's called the mastoid. And what they do now is they will play the same tones, but instead of acoustically, they'll play them mechanically or tactile, I guess, in a tactile manner, and it'll vibrate your skull. And now what we're doing is, if you follow this blue dot, roughly where the bone conductor will be placed, we start vibrating the skull, and we bypass the entire acoustic portion of the ear, bypass the middle ear, and we go right into the cochlea for processing. So you can see why audiologists might apply this if they suspect middle ear damage to see if your cochlea is still functioning. But the reason why I bring this up is, I think more and more we see different ways to enhance acoustic performance, and especially in things like high noise environments where intelligibility can be really poor, let alone speech quality. And we see people experimenting with things like, tactile sensors and vibration transducers to enhance at least low frequency waves, which maybe you don't have a fantastic transducer like in a mobile phone, or there's just a limit to how much bass energy you can get out, and you can compensate for that and work in tandem by using vibration to accomplish similar things. So let's move on, because speaking about headphones, the thing about the ear as well is it presents a unique acoustic impedance scenario that we don't see in a free field environment. So if you're familiar with the physics of free air, we have roughly 410 acoustic ohm across the spectrum in free space. And so if you put, let's say, a pair of headphones on a tabletop facing up, and you stimulate them with a frequency sweep of equal magnitude, and you just put a reference microphone out in front. Remember, very small reference microphone, doesn't really influence the sound waves, but you just measure the output of that headphone driver out into free space. You're exposing it to 410 acoustic ohm, and you get a certain response. Now you take that headphone, you put it up over an ear, and all of a sudden, the acoustic impedance inside this relatively small closed cavity, right? You have the pinna itself, the concha bowl, or the cavum concha, the ear canal, presents a vastly different acoustic environment than what you saw in free space. And the response, therefore, of that transducer, of that headphone transducer, is going to differ from what we saw in free space. Now, once again, why do we bring this up? We bring this up because if you look at some of the test equipment out there, there are mannequins that have vastly different shapes of ears and ear canals, as well as transducers. Some of them have microphones right at the ear entry point. They're suitable for anything in the far field. And then we have the mannequins that have an ear canal and an ear simulator, and those are suitable for the stuff that go in the ear and on the ear. The primary reason is that acoustic impedance, the fact that it mimics what a human ear would do. Additionally, the way that, for us at Head Acoustics, we use calibrated headphones that are calibrated on a head and torso for orally accurate playback. And we do those calibrations on a head and torso with a ear simulator built in with an ear canal and all that. Now, sort of a neat point, if you suspect that there is clipping in a signal and you put your headphones on and you're trying to listen to it, you could actually take the headphones off, put the headphones on the table. Because of different acoustic load now, when there is clipping in the stimulus signal that you're playing through the headphones, you should actually be able to detect it a lot more easily if the headphones are now in free space, as opposed to clamped onto your head with a vastly different and vastly higher acoustic impedance. So try that next time you have a signal, a measured signal that you suspect has some clipping in it. Now, if we move into the inner ear, what I would like to draw your attention to is the fact that our cochlea is that snail-type organ, and if we were to stretch out the basilar membrane in a linear fashion, you'd end up with something that mimics a piano or a keyboard, where the high-pitched notes are all going to stimulate the hair fibers on the basilar membrane really just at the entry point of the cochlea, but they don't travel that far down. They just don't have the energy to do that, or the wavelength to do that. Whereas the low frequency ones, or the low pitch sounds, they do stimulate not only the hair follicles or the hair cells at the front of the basilar membrane, but all the way down to the apex or the end of the cochlea. And so, in some ways, if you take that membrane, stretch it out, and imagine it as a keyboard, we can imagine pushing different keys and stimulating different portions of the cochlea. Now, this webinar is not supposed to get into psychoacoustics, but I did want to draw your attention to a few elements where some of the non-linearities that we see in psychoacoustics could potentially be traced back to some of the physical stuff. If we talk about frequency aspects first, the shape of the cochlea and the way that we only have stimulation of quite a few hair cells at higher frequencies actually means that our frequency resolution, this is a known fact, but the frequency resolution is worse at higher frequencies. So if we go back to our piano layout and you look at the different keys on a piano, I think there have been multiple studies that if you hit the A4 key, about 440 hertz, right here, and you were able to generate a 441 hertz tone from a loudspeaker, you would be able to distinguish between that 1 hertz difference. And at low frequencies, remember, we're stimulating a lot of the basilar membrane. Basically, we have a lot of data points in our cochlea to determine exactly what frequency is being observed or heard. Now, if we go to the very higher frequencies and we play out, let's say, a 4 kilohertz tone and a 4001 hertz tone, so again, 1 hertz difference, you would not be able to detect the difference between the two like you would if we were down much lower in the frequency range. And if you go back to the cochlea and you think about how it is spaced and how few hair cells and how few data points we now have, I think there's an argument to be made that the cochlea, the way the physics of the human body and the ear is constructed, we have a just a reduced sense of sensitivity or resolution at the higher frequencies. Now, additionally, or maybe in tandem to that, part of the reason why we use a logarithmic frequency scale or axis typically is because of the way the human hearing works, and that it is not linear. And you can easily tell here from the way 1 octave is spaced down at the lower end with about 30 hertz of separation, whereas at the higher end, you're talking 2 or 3 kilohertz in what separates 1 octave. And again, our hearing, our sensitivity of our hearing is similar. And we'll touch on that next week when we talk about octaves versus FFTs and how to analyze data. Now, going back to the level side of things, obviously, our dynamic range is enormous, anywhere from about 0 dB SPL, which doesn't mean no sound. 0 dB SPL just means it's roughly 20 micropascals, or 0 dB reference to 20 micropascals. So there's still pressure fluctuations below that, it's just that we can't perceive them. And then up to about 120 dB SPL. That's on the high end, that's sort of the threshold of pain. We can hear sounds higher than that, but they're painful and could lead to hearing damage and worse. And you guys know, roughly, that 10 dB is perceived as a level doubling, right? So if you increase the sound by about 10 dB, you will perceive it as the sound level or loudness has doubled. Now, there is such a thing as a cochlear amplifier. And what the cochlear amplifier does is it actually works at all levels, but it's particularly noticeable at the lower levels. And what it does is it basically amplifies the effect of the vibrations in the basilar membrane, so that lower levels are going to be perceived a little bit louder. So that 10 dB doubling rule does not apply at the lower levels. I guess I would equate it to if you have a sound pressure event that is the equivalent of a paperclip in weight, the cochlear amplifier will add the equivalent of another paperclip. And so you get sort of a doubling of the sound, and you can perceive it much, much better. Now, at very high amplitudes, let's say the sound pressure level is equivalent to a Boeing 747 airplane, the cochlear amplifier is still there, adding a paperclip's worth of weight to that sound. It's just, you're not going to notice that. But it means that this 10 dB level doubling, not that we normally associate with things like super loudness and other metrics, doesn't hold true for the extremes, especially at the lower levels. And ironically, at the higher levels, the cochlear amplifier also means that it sort of helps us govern our frequency masking effects in the ear. And that means at higher amplitudes, our frequency masking actually gets wider, and our sensitivity, as we talked about, to individual frequency tones, also becomes reduced at higher levels, which is ironic when you talk about, music concerts being ridiculously loud. You actually have less sensitivity and perhaps less appreciation for the individual notes that are being played out. Now, I think you've all seen the equal loudness curves, contour curves before. And in some ways, that low frequency stuff, you see the compression down here at very low frequencies. We're not very sensitive to it. And then right here at 1K, you see that's where the fawn curves are based out of. That is supposed to be sort of the threshold here of human hearing. And this is roughly the pain threshold. And you can see it's not a linear experience. We don't experience all frequencies the same. Now, quick question. What happens here at 3.5, 4K? This is where our hearing is actually the most sensitive. What frequencies do babies cry at? I think all the mothers in the audience can probably say, oh, absolutely 3.5K. And sure enough, babies put out a lot of energy when they cry, right in this 2 to 4K range. Likewise, fire alarms, actually, a lot of them designed, a lot of them designed to put a lot of wake people up. You should put out energy down at 500 hertz. But be that as may, that's where we're most sensitive. Now, how do we tie all this together? So the point is that the standards groups long ago got together and said, we have to have a way to simulate human beings in a sound field as best we can. One of the ways to do that, according to ITU-T P58, is to have something that has roughly the same HRTF, the same free field and diffuse field equalization curves, that interacts with the sound waves the same way, that generates the same diffraction effects to sound waves. And so I'm not going to read this verbatim, but you can see that's the scope, that is literally the intention of ITU-T P58. And so we have 2, 3 mannequins on the market that complies with that. The whole idea is we now have a representation of a human body. Taking a step further, P57, same thing. We need something that looks and behaves like a human ear, because once you get higher in frequency, that's where we start to see the ear dominate more than, let's say, the overall shape of the shoulders and the head. And as we keep stepping through now to the middle ear and the inner ear, you'll see that there are also standards that govern this. This one's been around for about 40 years. It used to be the IEC 6711. It was then later changed to 318-4, but it's the same thing. It simulates the ear canal impedances, the transfer functions, and the overall response of the middle and inner ear out to about 10 kilohertz. And now finally, going back to where we started with that tree in the forest, if there's an event out in free space, how are we supposed to reproduce that event in an accurate way? Well, once again, at least in telecom, there have been a lot of standards to govern how we do that. And one of those is the ETSI TS 103224 standard that basically creates a background noise sound field that not only is able to reproduce the magnitude over frequency out to 20K, but also has methods in there that allow you to equalize the phase information out to about 1.5 or 2 kilohertz, giving you more of that spatial information. So it would be as if you were standing, let's say, at a train station or in the woods and a tree falls down. So let's wrap this up, put a nice bow on it. We're coming up on our deadline here. But the message that I want to leave you with is that, first of all, the human sense of hearing is extremely fascinating. There's a lot of cool stuff in here that not all of it is really applied to telecom, but I think with a lot of these industries that are bubbling up here with augmented reality, hearables, even sophisticated conferencing devices, there's still elements here that we can take advantage of to improve the experience for the user. And the human sense of hearing obviously is the foundation for a lot of what we do here. You know, we are involved in audio and acoustics. You are as well. And it really is the foundation for everything we do. Now, we are, of course, a fantastic transducer. Our ears are generally very, very good. And our brain is an even more fantastic analyzer than anything currently available. Why does that matter? It matters because if you have measurements or algorithms and you don't quite believe what's going on, try and listen to it. You'd be amazed at how much you are able to detect and discern using your own ears and your brain for interpreting those results. And so use that to your advantage. So with that, I would like to say thank you very much for attending. It's been a pleasure. We hope to see you at the next webinar.